Hello, welcome back to your dynamics of rigid bodies. So we are still on your module 2, applying the principles of dynamics. Okay, and we discussed in your previous video your unit 1 and unit 2. Okay, and now we will proceed with your unit 3. By the way, in your unit 1 and unit 2, we discussed there your uniform rectilinear motion and uniformly accelerated rectilinear motion. And number 3, okay, let's try to discuss what are these motion curves. Okay, we say motion curves. Okay, we will define that one as we go on the next slides. Okay, so in this unit, you will be able to apply the principles of integration and differentiation of kinematic and differential equations. And of course, draw your motion curves of kinematic equations. So again, what is that motion curves? Okay, so if we say motion curves, it is often useful to utilize pictorial representation of kinematics using graphs. Okay, especially when the position of an object can be described by a differential equation of a curve. Okay, so actually, if you will try to look at the process just like we derived before, wherein if you have there your position, okay, if you have there your position, differentiate that one, differentiate your s with respect to time, that will give you your velocity, isn't it? And then if you have their velocity, differentiate that one with respect to time again, that will give you your acceleration. And then of course, if you want to bring it back, integrate, of course, because integration is the inverse of your differentiation. It is the antiderivative. So if you want to bring back your acceleration to velocity, then integrate that one, and velocity to position, integrate that one. Okay, so motion curves. So again, what is motion curves? These are your pictorial representation of kinematics in using graphs. Okay, we are going to draw that one using graphs. Okay, so note it says there that in mathematics, a line is considered the first degree. Okay, that is your basic of your analytic geometry. If we say line, that is a first degree. If you are going to draw line, okay, that is just a straight line. Okay, so motion curve. Okay, so this is your first motion. Okay, motion with constant velocity. Let's first have your motion with constant velocity. So if we are going to draw the graph of this, first is your position versus time. Okay, we are going to graph the equation of your time and position. Okay, so if we are going to graph that one, as time progresses, okay, if there's we are talking here of constant velocity, your velocity is constant. So as time, okay, as time elapsed, or as time goes on, the distance that we are traveling also rises, isn't it? As time goes on, your distance also increases, of course, because you have there a constant velocity. So that is just actually, you are going to plot that one, that is just a straight line which is inclined. And recall that if we have there your distance and time, all you need to do, if you have the equation there of distance and time, you will just differentiate that one, that will give us your velocity. Okay, so this is your motion curve, or we call this one the drawing or the graph of your time and position as constant with constant velocity. Okay, the same motion with constant velocity still, but this time we are now going to plot the drawing of your velocity versus time. As we said a while ago that your velocity is constant. So if there is a certain velocity that is constant, so all throughout the time that is constant, that is the same all throughout the time. So that is just the representation of that in graph. It's just a straight line which is horizontal. Okay, it is higher than your t because there's a value. Let's say, isn't it? If you are going to plot that one, that is from 0 going up, from 0 going to the right. So again, this is constant velocity. That is the graph. It means that it's just a horizontal. Okay. And again, if you want to get your acceleration given your velocity and time, just differentiate that one with respect to time. You will have your acceleration. Okay. How about your acceleration versus time? Since if there is a constant, when do we have a constant velocity? When do you have a constant velocity? If there is no acceleration, isn't it? So the graph of that is of course just a straight line which is 0. equal to 0. So the acceleration is 0, isn't it? So that is your acceleration versus time in constant velocity. Okay, but this is another. Actually, there are a lot of what do you call this one? Lot of parameters. If you will now continue differentiating your acceleration and so on and so forth, you will be having a lot in physics. You will be having a lot there of terms defining what are these parameters. However, okay, we do not need actually all those ones. So let me just discuss to you your what if I will differentiate. Okay, if we will now to differentiate again that acceleration with respect to time again, that will give us your j. We call that j as the jerk or the jolt. Okay, it is a change in acceleration over time period. But in here, we will not be actually applying that one in engineering. Okay, in this profession, we will not be needing those one. So I just introduce you that one, but actually we will not need that one. Okay, but the point there is, okay, look at this. Okay, look at that. Acceleration versus time in a constant velocity is 0. Velocity versus time in still constant velocity, there is no value, but that is straight line. We call that one 0 degree. Okay, 0 degree because it is a flat line. And then motion curve of this position time of still constant velocity, that is now an inclined line. If we say inclined line, the degree of that is first degree. Okay, so again, the degree from 0 from no equation at all to 0 degree to first degree. Okay, so by the way, if you are trying to differentiate, what happens if you are trying to differentiate, isn't it? Let's say originally that is x cubed. Differentiate that one, that will now become x squared, and then differentiate again. So as you can see, the degree is reduced. Okay, the degree is reduced if you are differentiating, and that is what happened here. You have originally your position, differentiate that one, that will reduce the degree. So first degree, it will now become 0 degree. And if you will further differentiate that one, that will now be 0 at all, or no equation at all. Okay, that is only for constant velocity. How about if we will now, this is, if you say constant velocity, that is, what do we call this one? Uniform rectilinear motion, isn't it? How about if now, let's proceed with your constant acceleration. So that now falls under your uniformly accelerated motion. So that is now where we are, uniformly accelerated motion. Let's try to investigate the motion curves of this. So again, as I've said a while ago, as you go on differentiating from position, the degree is reducing. Okay, so, or as you go integrating, you are bringing back, or you are adding degree. So I think it is better if, okay, sige, let's start with your position in time. So if you will try to draw that one with a constant acceleration, okay guys, so we have now an acceleration which is constant. So if you are going to draw the curve of that, the equation of that, that is actually a curve which is actually a second degree. Okay, that curve is second degree. It means the power of that is squared. Okay, if you are going to differentiate that one, I will reduce the degree of that. I will reduce the degree of that. So if that is originally second degree, if I will differentiate that one for us to get your velocity versus time, which is here, that will now be first degree, which is again an inclined line. Okay, and then if I will differentiate it again to get your acceleration, that will be from first degree, it will become 0 degree, which is a straight horizontal. And actually that is true because we are referring here to acceleration, constant acceleration, uniformly accelerated motion or constant acceleration. Okay, that's it. That now represents. So again, if you will try, again, look at this. Second degree, differentiate. First degree, 0 degree. Okay, if you will try to bring it back 0 degree, it will now become first degree, second degree. Okay, so that, just remember, just do not forget about your differentiation and integration here. If you have a position, just differentiate that one, you will have velocity. If you have velocity, differentiate that one, you will have acceleration. And but if you will further differentiate acceleration, jerk, but actually we do not need, but I only introduce to you what will happen. Okay, what else? Isn't it? There are three. Okay, the uniform rectilinear motion, that is uniform velocity or constant velocity. And we have your uniformly accelerated motion. There is a constant velocity acceleration. And then you have there your variable acceleration. Okay, rectilinear motion. So that's it. This is now the motion curve of that, the variable accelerated motion. Okay. So if a while ago that is your position time in the uniform accelerator, uniform rectilinear, that is what we call this one, first degree, and in uniformly accelerated, that is now second degree, you will expect that in variable acceleration, that is now third degree. Let's say this is third degree. Okay. So we will try to get your velocity versus time, differentiate that third degree, it will become a second degree. Okay, by the way, if we say degree, the curve will just become sharper and sharper, but actually it depends. But in these simple equations of motion, the curve will just become sharper and sharper. As the degree rises, the curve will just become sharper. Okay, so velocity in time, this will be a second degree. Okay, from third degree to second degree. And then since variable, that is first degree. Since your acceleration is variable, that means it is, let's say that is uniformly changing. But actually, in the true situation, in the actual situation, if you are actually, let's say, driving a car, maybe your acceleration is changing, isn't it? But let's just consider the ideal situation, wherein you will try to increase your acceleration, which is in a uniform motion or uniform characteristic, so that will form a straight line. So the point there is that, okay, again, position third degree, differentiate that one in velocity second degree, and then differentiate again for acceleration is first degree. Okay, those are our motion curves. So what does that mean? Okay, where are we going to use this motion curve? So for example, okay, in your case, you have there a variable acceleration. You have there a variable acceleration, and you have the equation of your velocity versus time. All you need to do is plot that one, draw the curve of that, and then all you need to do now is, let's say at this time, at this certain time, what is the equivalent velocity? Just go to the curve, get the equivalent velocity. That's it. That is your velocity within that time. Let's say another time, go to the curve, get the velocity. That is the equivalent velocity. So that is the use of your motion curve. If you have a motion curve, okay, you will now actually what do you call this one? Anong tawag doon? You will actually be needing this one, okay? Especially if you will have variable acceleration. Okay, we will look at that later on. If your flow of motion is not just single, let's say this is the flow for this period in time interval, and then from this point in time, the flow of your motion will be different. Okay, so if you might be thinking there, okay, why do I need to draw this motion curve if ever? Okay, why do I need to know about that if I already know my equation? So if you already know my equation, all I need to do is solve that one since I already mastered. But again, the point there is, what if there is in this time interval different type of motion, in this time interval another different type of motion, and so on and so forth? What if there are different motion in such a certain time interval? So you cannot say, okay, I will investigate the acceleration, velocity, and position in this motion, proceed, and then proceed, and then proceed. You will be having a lot of solutions. So that is how, when you will be appreciating, that is my term a while ago. Okay, that is when you will appreciate your motion curves. Okay, so let's have here, let's have here an example. Okay, yeah. But before going to the example, by the way, okay, how are we going to make use of this motion curve? Okay, the use of this motion curve is if we are going to establish acceleration, velocity, and position by merely focusing on if you already plotted your curves, you can just focus on that curve you can forget about your formula and then focus on the drawing, and then you can get whatever you want there. Okay, that is your motion curve. But how are we going to deal with that? Is by area method. Okay, area method to establish your motion curve. How are we going to draw? Let's say you only have there originally your acceleration versus time. How will you establish your velocity versus time and then position versus time? Because let's say you are given the acceleration, but you want to get your position, you want to get your velocity. So therefore, you need to have your three diagrams, motion diagrams: your acceleration time, velocity time, and then position time. So how are we going to establish if you are given one? Let's say you are given your acceleration versus time. Okay, so for example, this is your drawing for that. You have this acceleration versus time. How will I draw the motion curve of my velocity versus time? Okay, let's try to consider here. Consider A given and then AT diagram. Okay, given AT diagram. Okay, the acceleration, the AT diagram is given. Okay, and do not forget that your A is equal to dv over dt. Okay, isn't it? That acceleration is the derivative of velocity versus or with respect to time. So since A is given, that means that is constant. So if let's say A is given, that is constant, then I will play around with this equation. Okay, we want to get, of course, we have your acceleration, so we want to get your velocity. Cross multiply for us to go back, isn't it? Position, differentiate, velocity, differentiate again, acceleration. But if you want to go back, integrate and then integrate, integration. So our process here is integration. Cross multiply, okay? dt will go with a. So you have here dv separated, and on the other side is a dt. Since a is given there, that is a constant. Okay, so integrate both sides. Integrate your dv again. We are integrating using your definite integral. We are considering time interval, so there should be a limit. Okay, so from original velocity v sub o to your v sub n. Okay, if you say v sub n, that could be any time. Okay, we will not just focus on v sub f or final, because let's say we are considering such time interval in between. So let's say from original to, okay, for example here, okay. Oh, my bad. I need to change that one. Okay, so that's it. Let's say again, you have here, you are given here your acceleration versus time diagram. How are we going to establish your velocity versus time? So again, integrate. Okay, integrate this one, this resulting equation that we tried to have a while ago. But since we are considering here, okay, such, let's say we are considering this time interval at t sub o and t sub n. Let's say this is the original time and that is the time, the final time that we are considering in between your motion. So let's say we are just referring to what is the velocity from to to tn. So what is the change of velocity? Okay, so if we are going to integrate this one, you will be having here v, of course, that will be, but substitute your upper limit minus lower limit, which is v sub n minus v sub o. Okay, that is your v sub n is your velocity at t sub n, and v sub o is your velocity at t sub o. And then integrate your other side. Since a there is just a constant, integrating this one, that will just be a times t. However, substitute your upper limit, which is tn, and then lower limit to. You will have here a times tn minus to. So the point there is, this resulting equation explains to us that v sub n minus v sub o, it means that is the change of velocity from tn to to. Okay, it means that is the additional velocity from this time going to that time. Okay, since in this, let's say in this, for example only, in this diagram, that is a constant acceleration, so therefore there will be a change in velocity from time o to time n. So the question, what is the additional velocity from time o to time n? Isn't it? So that is your v sub n minus v sub o. That is your velocity here, and then minus the velocity there. So that is your additional. So how do we get that one? By integration, okay, or I mean by motion curve. Since it is revealed to us by this equation, v sub n minus v sub o, which is the change in velocity, is just equal to a times tn minus to. So if you will try to look at our drawing here, if you are going to look at the drawing there, that is actually just the area under your curve. Okay, So A there is this one, is this height, and that Tn minus To is actually the base of your rectangle if you are considering a uniform acceleration. But if that is, let's say, that is a variable acceleration, it means that your drawing here should be inclined, then still you will be getting there an area of trapezoidal, isn't it? You will be getting there the area of trapezoidal. So you will be having an acceleration here, a different acceleration. So that is just geometry. You can solve the area of that. And again, the area under that curve is the change in velocity. Since this is acceleration time diagram, the area under that is the change in velocity from T sub O to T sub N that we are considering. Okay, so that's it. Now, how about if we already have now your velocity time? So again, actually this is not the velocity time diagram from this. This is your acceleration time. This is constant acceleration, but this is actually not its velocity time. But for only example, so that you can visualize. Example, let's say you have here your velocity time, and you want to get your position time diagram. Okay, for example only, okay, for example, these diagrams are not related. This is only for example. So actually, if you try to look here, this is constant velocity, so that is in your uniform rectilinear. So how do we get your position time from velocity time? Okay, so the same. Let's start now with velocity is equal to ds over dt. So again, let's say v there is given, therefore it is constant. So v is equal to ds dt, play around with that. Okay, you will have ds equals v dt, integrate both sides again. We are considering a time O to time n. Okay guys, time O to time n. Then, again, the area under that, okay, of course, the same process here, you will be integrating. So you'll have Sn minus So, that is the change in position from Tn to, from To to Tn. Okay. So how is that again? It revealed to us that that is just the V times the change in time, which is actually the area here. So the area under this curve. So again, that is how we establish your position time from velocity time. Okay. So acceleration time, get the area under that one at any interval. That is the additional velocity in your velocity time diagram. Okay. From the time interval that we are considering. If you have their velocity time, the area under that in such interval is the change or the additional position given that interval. Okay, so that is your area method in your motion diagram. So let's have an example. Okay, so example number 1. Okay, let's have only one example and then you'll have an activity. This is just simple. Drawing your curve and then solving the areas. Okay. Okay, so that's it. So let's say given AT diagram, plot the BT and ST. Because again, once you have your diagrams, you do not need actually to be using your formulas. All you need to do is get the area, draw the curve, and then find out in that drawing the value of the velocity, acceleration, and position at a given certain time. Okay. So let's say this is now given your AT diagram, means this is A versus T. But again, this is just like formula. If your acceleration is in this unit, you need to make your time coincide with the unit of that. So let's say meter per second squared, since that is acceleration, you should have their second. Let's say that is meter per minute squared, then you should have their minute. Okay, they should be aligning with each other, the units. Okay, so at time 0 your velocity is 0 and distance is 0, of course, since we are considering here the initial point. The initial point is at time 0. So if you'll try to look here, this is just the explanation actually, but if you'll try to just focus here, the areas I've said a while ago, the area, okay, in this given, since this is by looking at the drawing of your acceleration, it means that these are two different motions. The first motion from 0, okay, that is 0 of course, from 0 time to 2 seconds, that is in seconds, so 0 seconds, or from the initial to 2 seconds, your motion is since this is in 80, your motion is constant acceleration or uniformly accelerated, tama? And then from 2 seconds to 4 seconds, there is a release. So that's why you have here a going down. Okay, that is just the meaning of that. Your acceleration is decreasing as time goes on. It means that you are, let's say, you accelerated at a constant speed, and then now you are releasing the acceleration. Okay, you are now releasing the acceleration. So that is the meaning of your curve. So it means in this one, it is a uniformly accelerated motion. However, in this part or in this interval, it is now a variable accelerated motion. So that is what I'm saying. That is the advantage of your motion curve. You can consider all of them, all of this motion from time 0 to the final time. Even if these are different types of motion. But if you only limit yourself on formula, what you're going to do is solve whatever you want to solve in this motion, and then proceed here to solve whatever you want. So you will be dealing with equations here and different equations there. Let's say there are 5 intervals with different motions. You will be solving 5 times with different formulas. So what if you forgot, you interchange formulas, then there will be a complication there. So that is the disadvantage of only knowing your formulas. And this is the advantage of your motion diagram or your motion curve. Okay. So now again, as I've said, the area under your acceleration time is the change of velocity, okay, from the given interval. So let's say from 0 time to 2 seconds, okay, from 0 second to 2 seconds, if you will try to get the area here, okay, by merely looking at the values, this is 4, so the height of the rectangle is 4, and then the length of that is 2. So if you are going to multiply there, actually, okay, here, that is acceleration. So 4 meters per second square, multiply your time, which is 2 seconds. Second and second cancel, so you are just left with meter per second, which is 8 meters per second. It means that is a velocity, isn't it? That is the change of velocity from time 0 to your 2 seconds. And then from 2 seconds to 4 seconds, get the area of that. That is just a triangle, right triangle. So your area is just 1/2 base times height. Your height is the same 4, but multiply that one by 1/2, or that is 0.5. And then the time interval or the length of time or the base here is 2 seconds also. So multiply that one, it will become again speed. 2 times 4 is 8 divided by 2, or multiplied by 1/2 is 4. So the area here is 4 meters per second. So it means, if let's say we are starting from originally here, okay, the velocity is here. So the velocity is 0, and then you will add 8 meters per second, and then you will add further your 4 meters per second. So that is your motion curve. Okay, that's our motion curves. So let's continue now. Given this, let's draw your, what we call this one, let's draw your VT diagram. So it means at time 0, what is the added? Okay, we are now going to plot your velocity in time. So at time 0, what is the added velocity? 8 meters per second. And this is now where you will be using what we discussed a while ago. This is constant velocity. Going to velocity, from acceleration, going to velocity, okay, we are going back, isn't it? We are adding degree. So we will go back there, okay? This is a uniformly accelerated. Okay, so this one, constant velocity. You will go to velocity that will be inclined now, okay? From 0 degree to 1st degree. So if you will go later on to your position time, you will be having 2nd degree curve. Okay? So that is from 0 to 2 seconds. From 0 to 2 seconds is 0 degree. You will now be having that as 8 degrees. So from time 0 to 2 seconds, you will be adding 8 meters per second velocity. Okay, that is what I'm saying. From here to there, you will now be having your 8 meters per second. But how will you know the drawing of that? Again, 0 degree, it will just become 1st degree. So that is just a straight line. Again, from 2 now to 4, okay, the area there that we solved a while ago is 4 meters per second. So from 2 seconds to 4 seconds, okay, from this point, since you already have the 8 meter per second, you will add that 4, which will, it will become now, okay, from 8, we will be adding 4, it will become now 12. But the question, what is the drawing of that? First degree, it will now become second degree. But, okay, please, do not forget about this. You should know about your analytic geometry. That is decreasing, isn't it? That is decreasing. So the equivalent of that in your, okay, that is originally this one, increasing. This is the first degree, n equals 1. The second degree of that, it will now be increasing. That is the meaning of your curve, increasing curve. So n equals 2. However, this n equals 1 is decreasing, so the curve of that is decreasing. It will still go up, but it will not be opening downward. So n equals, okay, that is the equivalent. So in our curve here, it will now be from 8 to 12, it will now be opening downward, which is a second degree because that is first degree. Okay, so we have now your AT diagram. This is the given a while ago. We will now be having your VT diagram, which is this already. But later on, we will be needing your position and time diagram. So now the question there is, how are we going to get that? The same. The area under your VT is the additional position in your ST. Okay, so the area here is the additional position from your 0 to 2. Okay, so we will always consider here, we consider that since there is no given initial velocity, initial acceleration, and initial velocity and initial position, we assume that that starts from 0. Okay, so that's it. So now, okay, we already established this one, but later on we will be needing the area. Okay, so let's solve it before we will proceed to your drawing of position time. So area of this, again, this is just a triangle. So again, the base is 2 times the height, which is 8. So again, look at this. If you will multiply that one, but do not forget to multiply by 1/2 since that is a triangle, isn't it? So if you try to multiply the base and height, your base is seconds, and that is meter per second, isn't it? Look at this. Second multiplied by meter per second, so actually second and second cancels. So you will end up with a unit of in meters, which is distance. That is your position. Okay, that is your position, meters. So now, what are we going to do now is, okay, Okay, multiply again, base times height divided by times 1/2, since that's a triangle, that will be 8. 2 times 8 is 16, divided by 2 is 8. Now, we will get the area of this one. That looks like complicated actually, but if you will try to look at this, that is just a rectangle plus the curve here. So, okay, again, this is where the analytic geometry enters. Okay, I will show you how we solve the areas of the curve. So, okay, let's say originally we have here triangles. Okay. Let's say that is a triangle. That is just half of this one. So that's why, let's say this is base times height. Base and height. Base and height. So this is a first degree, isn't it? N equals 1. So the area here, the area there is 1/2. Base times height. Isn't it? That is your analytic geometry. How if that is a curve? Okay. Please do not forget about this. This is very, very important. Wherein this curve is a second degree curve. The area, okay, the smaller area, let's say that is considering the whole rectangle. The area or the area which is actually the back, or it is just like a triangle that is reduced. Okay, so this one, the area here is this one, the area here. These are the areas that we are considering. The area there is 1/3. It will now become 1/3 base times height. And let's say this is now a third degree. Okay, it is a little bit sharper. So again, we are referring to this area. This is third degree. That will be area is 1/4 base times height. Okay, so that's it. Please do not forget, that is very, very important basics of your analytic geometry. So again, a straight line n. So it is just like, okay, area is equal to 1 all over n plus 1. That is your basic or your general formula. So if that is first degree, that will be 2, 1/2. If that is second degree, that will be 2 plus 1, which is 3. Third degree, 3 plus 1, which is 4. But that these are, do not forget, do not interchange. However, in our figure there, what we need is this one. See that this one. Originally, that is just a rectangle. So your original area there is for the rectangle is base times height. But we are finding what we know, the formula is 1/3. So if you need this one, the area here, let's say this is your area 2. Say this is your rectangle. Area 2 is area of the rectangle minus the area here. Let's say this is area 1. Say that is your area 1. So, base times height minus 1/3 base times height. Then 1 minus 1/3, that is 2/3 base times height. Okay, so again, in here, if that is 1/4 base times height, then this is 3/4 base times height. Just like here, 1/2 base times height, since they are identical, this is also actually, if you subtract 1/2 and 1, this is also 1/2 base times height. Okay, very, very important. You will not just be needing this one here, you might be needing that one in the other subjects. Okay. So how do we get the area? This is just a rectangle again, rectangle. So that is just base times height, 8 times 2 is 16. In here, okay, again, as I'm saying, this is the second degree. So the imaginary reduced triangle on top is the 1/3 base times height. So the remaining here, okay, the bigger part here is, instead of 1/3, subtract that 1/3 with 1, that will become 2/3. Okay, so your formula here is 2/3 base times height. Your base is 4 and your base is 2 and your height is 4. Okay, so what is that? 4 times 3, guys, 4 times 3 is 4 times 3 is 12. 2. This is not 3. Sorry. 2 to 4, that is 2. So your base is 2 and your height is 4. So 2 times 4 is 8. Get the 2/3 of that. 2/3 of 8 is 2/3 is 16/3, or that is 5.333333. Okay, so let's just consider the whole number, 16/3. So later on, we will be needing the additional distance from 2 seconds to 4 seconds. I will add 16 and 16/3. Okay? So now we have your velocity time diagram. Now let's go. You have here your velocity time. Let's draw your speed or your position time diagram. Okay? So again, look at this. That is the first degree. It will now be increasing. This is increasing first degree, so it will now becoming second degree, which is increasing curve. Okay, I showed that one a while ago. And then this is decreasing second degree curve. It will become decreasing third degree curve. Okay, decreasing third degree curve. So this is still a curve. Okay, it only looks straight line since we are considering here just a 2 seconds, but if you will try to plot that, that will be a curve. Okay, so again, how do we ended up with this? How do we ended up with this drawing? Is the area here. Okay, the area here is, again, let's solve the area there. That is 1/2 base times height, which is 8. And we solved the areas here also a while ago, which is 16 and 16/3. So from 0 position, what is the additional from within this interval 2 seconds is 8. So 0 plus 8 is 8. So somewhere there is 8. Okay, so I will plot there and then trace that one. From first degree, it will become second degree, which is increasing. Okay, and then from this point, again, from this point, what is the additional position from 2 seconds to 4 seconds? Solve this one, add this one. So 16 plus 16/3. 16 plus 16 over 3. Let me just take that one. That is 64 over 3, or the decimal value of that is, wait, 16. Is that 16? 16 over 3. Okay, so 16 over 3, the equivalent of that is 64 over 3. But that is not what we are going to plot, since originally from 2 seconds you already have the 8. So we will still add 8 to the summation of that. Or that is just the accumulated area there. So plus 8. So that will become 88 over 3, which is in decimal 29.3333. Okay. So again, from 2 seconds, which is at this point 8, to that 29.333, we will draw that one using a third degree curve. So it is still just a curve going down or opening down, since this is opening down or decreasing. This is decreasing. So now you have your motion curves. So the point there is, where are we going to use these motion curves? Okay, let's say, you want to investigate what is the acceleration, the velocity, and time, let's say at 3 seconds. Okay, so what is the acceleration, the velocity, and time at 3 seconds? If that is the question, okay? So just get the equivalent of the 3 seconds. So let's say somewhere there, 2 and 4, the between is 3 seconds. So get the velocity there. I mean acceleration. So actually, if you try to apply ratio and proportion, that is between this triangle. So if that is 8, this will be 4. So acceleration in your 3 seconds is 4 meters per second squared. Now, what is the velocity of that in 3 seconds? So plot that one, and then 3 seconds, and then go to the equivalent on your curve. Somewhere there, you will be having something 10 or 9 or 11. Okay, somewhere there, you can plot that one and then investigate what is the value. Okay, and then what is the position? If you say what is the position at 3, then the same, using your motion curve at ST. Plot that one, you will go there somewhere at 20 or 20 plus or 20 minus. Okay, so that is how we will utilize your motion curves. Again, it will be very, very helpful if you have not a single type of motion in all throughout the movement. Okay, just like this. There are 2 types of motion from 0 to 4 seconds. Okay, so that is your motion curves, and then area method, establishing your motion curves. Okay, so try this one. Please try this one. This is a problem solving. That's why is it that in here you might be saying, why is it, sir, that your example you already given the AT diagram, and for us we are going to translate that first? Of course. Okay, I guess this is your transformation of worded to graph is not a problem, since you already finished your basic mathematics, isn't it? You're expected. That's why before you should be serious with your basic mathematics. Okay, so if they said that you should be serious with this subject, then you should do that. Okay, so that we will not be repeating and recalling again algebra, trigo, and so on and so forth in all your subjects. Okay, that's why that is prerequisite. It means you already mastered that subject before proceeding to the next. So you are given here a problem solving. Convert that one into a drawing, whatever drawing you can create from this, and then solve. It says there, find the total time. Okay, find the total time. That is the problem there in this motion. Find the total time, and then after that, draw your VT and ST diagram. Okay, so VT and ST diagram. Okay, so do that one. Okay, please, but first, do not forget, this is the important concept here. Okay, you can read that one. It is useful. It is often useful. This is the definition of a while ago, but again, I'll repeat. It is again often useful to utilize pictorial representation of kinematics using graphs, and especially when the position of an object can be described by a differential equation of a curve. So again, or in simple words, this will be very, very helpful, your motion curves, if you have different types of motions all throughout. Okay, and then do not forget this one. This is very important also. If you have position, differentiate, velocity, differentiate again, acceleration. If you want to bring that back, integrate and then integrate. Okay, this is the very, very important concept that we discuss here in your Unit 3. So thank you very much for listening, and then please comment below if you have a question or ask that one in our live discussion. Okay, so thank you very much for